So the last person that we want to talk about when we're looking at the speed of light, and we're giving a video just for his methodology, is that of Albert A. Michelson from the United States. So his work actually built on the work of someone else, which is pretty common in science. We're usually building off previous works. And he was building off the work of a gentleman named Jean Foucault from France. So Jean Foucault, he obtained a value for the speed of light of about 298,000 kilometers per second, about 2.98 times 10 to the 8 meters per second. Now that's pretty good. It's only 0.6% away from the current accepted value. But Michelson, he thought he could do a little bit better. And over the period of several years between 1877 and 1931, he did a lot of experiments to determine the speed of light. The one that we focus on gave him his best measurement for the speed of light, and this was in 1926. So what he obtained for the speed of light is he obtained about 299,796 kilometers per second, and an error of about plus or minus 4 kilometers per second. So the value he got, it's only 4 kilometers per second greater than the actual currently accepted value. So that's pretty significant. The margin of error is extremely small. The percent error is actually extremely small. Not only that, but the actual accepted value is within Michelson's results. It's within the parameters of his error. So Michelson actually did a heck of a job determining the speed of light. So his methodology is still kind of like a gold standard today. Obviously, it's been refined a little bit. So what Michelson did, and I'll show you this on a diagram. I'll show you this on the next page. So Michelson used this setup using an octagonal mirror. So this is kind of a very simplified version of Michelson's setup. So what Michelson had is he had this 8-sided mirror. Light was able to reflect off this 8-sided mirror. It was able to travel 35 kilometers away, travel back to this 8-sided mirror, and then somebody could observe this in a detector. Now for us, we're using a plane mirror. Michelson actually used a curved mirror. As I'll mention a little bit, we're simplifying Michelson's experiment just to make it a little bit easier at the high school level. Now, that's great that we have this set up here. The thing is, though, that doesn't really help us. We know the distance. Light travels 35 kilometers there and back, so we know a distance of 70 kilometers. But without knowing a time, this is not really helpful to us. So what Michelson devised was pretty ingenious. Now, Michelson noted that with his octagonal mirror here, if the mirror wasn't in this exact position as you see it here, the light was not going to reflect off the plane mirror. So you kind of see down here, the mirror is rotated a bit. The way light intersects, it's going to miss that plane mirror. What Michelson had thought to do in his experiment is, well, if we can get, so this side here, this is the side light's reflecting on, and it's going to hit the detector down here. Well, what Michelson thought of is, in the time it takes from light to go reflect off this rotating mirror to the plane mirror and back, what if we could get this side of the mirror, what if we could get that to rotate to this position right here? So what Michelson wanted to do is he wanted to time how long it would take the mirror to make 1/8 of a complete rotation. So in the time that the light took to go from the rotating mirror to the plane mirror and back, this mirror should be able to make 1/8 of a rotation, which is what we have here. And this allowed Michelson to actually determine the speed of light. He would have been able to control how fast this mirror was spinning, like he would have been able to control its period. So if he knew how long it took for the mirror to make a complete revolution or one complete spin, he could figure out how long it would take light to make to make 1/8 of a revolution. This would allow him to determine the speed of light. And we're going to look at a question like that momentarily. So I always get asked, how did Michelson know like he made it go 1/8 instead of like maybe a quarter or something? I don't know the answer to that definitively. If I had to take a guess, I'm going to say he just started spinning it really, really, really slowly and just kind of gradually increased the speed until he got sort of his first positive result. But I don't know that for sure, so don't quote me on that. So let's look at a Michelson question, like a typical Michelson question. So we're going to use the data that Michelson used. So we know that that distance between the rotating and in this case we're putting the curved mirror, we know that it's 35 kilometers. And we know the frequency of rotation of that mirror is 533 hertz. So with all the light questions, we have to be careful with the distance. So we know the distance between the rotating mirror to the curved mirror is 35 kilometers. So light is going to travel 35 kilometers there. But keep in mind, the light also has to come back. So it's going to travel back to the mirror another 35 kilometers. So for us, the total distance that we're actually going to use is 70 kilometers. Because the light has to go to and from 8-sided mirror. And that's probably one of the biggest mistakes that gets made on exams with respect to Michelson's experiment. Not making sure you're accounting for the distance properly. So that covers that piece. Now, we have the frequency of the rotating mirror. We also know from Physics 20, we know the period is just 1 over the frequency. So this is going to be that 1 over 533 hertz. And that is going to give us how long it takes for the mirror to make one complete rotation. So I'll just take some extra sig digs here. So the period of this mirror is going to be about 0.001876 seconds. So this is the time for one revolution, or one complete spin. Which is great information to know, but in Michelson's experiment, he didn't care about the time it took for the mirror to rotate once completely. He only needed the time for 1/8 of a rotation. So we only need time for 1/8 of a rotation. So if we know the period, to get the time, we're just going to take 1/8 of the period. So the time is just going to be 1/8 of that period. So for this, we're going to get about 2.345 times 10 to the minus 4 seconds. So that is the time it took for the light to, that's the time it took for the mirror to make that 1/8 of a rotation. So in this same time frame, what Michelson had wanted, in that time frame, what he's saying is that when this mirror made 1/8 of a rotation, in that same time frame, the light went from this side of the mirror, bounced off this curved mirror, and back to this side in that exact amount of time. So we know the time it took for the light to travel that full 70 kilometers. So the last thing to do is to actually get the speed. So again, we know the speed is v equals d over t. So we got that distance of 70 kilometers, or 7 times 10 to the 4 meters. And then we have that time that it took the light to travel that path. So we do something like this. We're going to get about 2.98 times 10 to the 8 meters per second. And like I said, this was Michelson's best measurement. And he was like, now we're cutting the numbers a little bit, like we're not getting to the same level of precision Michelson got. But yeah, with his experiment, he did a really great job at getting a very close value of the speed of light. And then of course, as we said, Michelson built on the work of Foucault, and then people built on the work of Michelson to refine his method. The big difference, and this is really simplifying it, the big difference between Michelson and Foucault's experiment is Foucault just had a rotating plane mirror. Michelson's the one who thought of the octagonal mirror. Now, as I mentioned, the big mistake here is we got to make sure that we account for that light going to the mirror that's far away and back. The only thing that they really try and do on exams to trick people with Michelson questions is they might say, oh, you don't have an 8-sided mirror. Let's say you have a 12-sided mirror. So in that case, you wouldn't want 1/8 of a rotation. You'd want 1/12 of a rotation. So you want 1 over what we call n. And you want 1/nth of a rotation, which is an n being how many sides of the mirror there are. So all that's really going to change is that time for the light to travel from the rotating mirror and back. So in this case, we used 1/8 because the mirror has 8 sides. If it has n sides, you're going to take the period, divide it by the number of sides to get the time frame. That's about all you're going to do. Now, you'll also see a lot of times when we talk about Michelson questions, we'll talk about Michelson-type experiments. The reason we're saying Michelson-type is this is broad strokes the Michelson experiment, but we've kind of simplified a bit of the analysis. So if I look at the diagram here, in Michelson's original experiment, if I recall correctly, the light bounced off the curved mirror, it hit like a plane mirror, bounced off the curved mirror again, and then went back to the rotating mirror. So certainly that's going to change the distance. The other thing is we're assuming this straight line path from the rotating mirror to the curved mirror is 35 kilometers. And actually that is the 35 kilometers, but the distance the light's actually traveling is along this path here. So that's going to change our distances. We also haven't accounted for the light coming from the source to the mirror, nor have we accounted for the light reflecting off the mirror to the observer. So our distance of 70 kilometers is not quite the whole story. So we've kind of cut short the distance a little bit. We've also kind of not accounted also for the time for the light to go from the source to the mirror and from the mirror to the observer. Now those times would be very minuscule, but that would certainly affect the level of precision. So we're looking at Michelson broad stroke. We're not looking at it exactly, but Michelson is the one experiment in physics 30 that you actually have to know about, and we can ask you questions similar to this on an exam about it. The other type of people, the other people like Fizeau, Romer, Hawkins, you're not going to be asked questions explicitly about them. What I've seen in the past is on a diploma they might say, here's some various scenarios for measuring the speed of light, and they'll describe them with words, and then they might just ask you to rank their accuracy. That question I've seen, it's not actually meant to be hard. Michelson's the one you have to know in more detail though.